Today we are going to talk about experiment number 8, which is transient circuit analysis. In this experiment we will talk about two different circuits. The first one is the series RC circuit and the other one is the series RLC circuit. In the series RC circuit we have two components, a resistor and a capacitor, that are connected in series with a DC source. It is important to note here that in this circuit initially the source is disconnected and the capacitor is fully discharged. As soon as we connect the source with this circuit, some current will start to flow in this circuit, and as a result the capacitor will begin to charge. The capacitor will take some time to charge fully. In order to understand the way this capacitor is charged, we will have to write the differential equation of this circuit. When we write the differential equation and solve for VCT, we find that this is the expression for VCT. And the way VC, which is the voltage across the capacitor, increases is shown in this graph. We can see that the capacitor charges gradually and it takes some time to reach to the complete charge. Actually, this graph can have different forms. For example, this VCT could increase slower than the graph that was shown earlier, or in some scenarios VCT could actually increase very rapidly. So this behavior is actually controlled by the values of R and C in the circuit. In order to understand this behavior, let us look at this equation. In this equation we have this exponential part. The sooner this exponential part decays, the sooner this VCT will reach to its maximum value. And we can see that in order for this exponential signal to decay fast, the value of RC should be small. So when RC is small, VCT will increase rapidly, and when RC is large, VCT will increase slowly. So this means that RC plays an important role in determining the behavior of VCT. We define RC as our time constant and we use tau to represent this time constant. We say that tau is equal to RC is our time constant. In this experiment, we are going to select some values of R and C and record the values of VCT. The values that we will record of VCT, we will use them to actually estimate the time constant tau.
Okay students, so we have seen first order series RC circuit. Now we will move to second order series RLC circuit. In second order circuit we have both capacitor and inductor. And why it's called second order? Because if we try to write down the the differential equation of this circuit, that will be second order differential equation. Okay, now students, again we will focus on the voltage across the capacitor, and if we try to solve that second order differential equation and try to find a solution for capacitor voltage, we will get this type of solution. So the solution has three different possible forms. These will depend on the values of alpha and omega naught. Now alpha and omega naught, they are defined as these expressions. They depend on the values of R, L and C. For series RLC circuit, alpha is equal to R over 2L and omega naught square is 1 over LC. Now if alpha square is greater than omega naught square, we will get this solution: Vf plus A1 e raised to the power S1t plus A2 e raised to the power S2t, where S1 and S2, they are the roots of the characteristic equation. We will see them shortly. And if alpha square is less than omega naught square, the capacitor voltage will have this type of solution, where we will have, you can see, we will have sinusoids. And at last, if alpha square is equal to omega naught square, we will have this type of solution. You know these solutions from your 202 course. Okay students, so now let's see what is S1 and S2, particularly which was defined in the first possible solution. S1 and S2, they are the roots of the characteristic equation, which basically arrives if we try to take the Laplace transform of the second order differential equation and find the roots, we will get these roots. Now we can also see that in the first possibility, if alpha square is greater than omega naught square, roots will be real. And in the second case, when alpha square was less than omega naught square, then we will have negative inside the square root and the roots will be complex conjugate of each other. And finally, if alpha square is equal to omega naught square, we will get same roots, equal roots. Okay students, now we will try to see the plots for the voltage across capacitor. So since we have three possible solutions, so we will see the plots for all three cases. So as we have assumed in the previous first order series RC circuit, we will assume here also that voltage across the capacitor was 0 initially. So there was no voltage across the capacitor, it was not charged. And when the source voltage was connected to the capacitor, capacitor will get the full voltage across it, and but it will have some transient response and it will take some time to go to the voltage V. In the first case, if we try to plot this, it will look like this. This response is called overdamped response, which is in black color. In the second case, which is in blue color, the response will look like this. You can see that we have sinusoids here, so that's why we see the oscillations, and finally it will settle down to the voltage V. In the third case, which is in green color, the response is called critically damped response, and it looks like this. Compared to the overdamped response, critically damped response rapidly settles to the final value V.